Okay, so we're going to go into programming with OpenMP offload on the AMD GPUs. So why do we want to use OpenMP to get our codes to run on GPUs? And the big motivation is that it's a well-recognized, standardized language, so we're going to have good portability. It supports Fortran, C, and C++, and there's not many options that will work with all three languages. So you can write part of your code in C++, part in Fortran, and often with big physics applications, you will have one team that would prefer to write in Fortran and another that would like to write in C++. And this allows them to work with the language they're most comfortable with. Many HPC codes already use OpenMP for threading on the CPU. And that actually is very helpful because it's got this idea, what we call fine-grained parallelism, where the loop can be broken up to work in any order. And if it's safe for threading on the CPU, then it's going to be safe to work on the GPU. That step actually is quite useful to get things running on the CPU first with threading. And we actually recommend using OpenMP for the vast majority of your code just because it's faster and easier to maintain. And if you need to drop to a lower level language like HIP or ROCm, it's interoperable with that. So we can just take a couple routines that we really need performance and write those in that lower level language. You can also compile this GPU code for the CPU by giving it a special target. And that can make it possible for you to print out what's happening. Maybe the debugging is a little easier there. So there are two major compiler strands today. And the first one, we're going to focus on LLVM, but the other is GCC. And that has probably most of the packages on your computer are built with GCC. But AMD is a strong supporter of LLVM. And LLVM is much better at offloading to the GPU. And you might say, well, these other compilers, I think, are better, but look at what they've all done in recent years. Intel is now using LLVM for their compiler. NVIDIA is using LLVM for their compiler. Almost everybody is moving to LLVM for their base infrastructure for their compiler. And the reason is because they can't keep, even Cray is now moving their C and C++ to LLVM. And it's because they can't keep up with all the changes in the standard. It's just impossible for a small compiler team. So we're seeing a lot of higher level HPC compilers moving to LLVM. AMD has been working with LLVM for longer than any other vendor, so they're quite integrated with the LLVM team. And so we have two compilers we use out of LLVM. One is HipCC and the other is AMD Clang. And AMD Clang is for OpenMP offloading. HipCC is for HIP and ROCm lower level programming. They both call the same LLVM compiler. They're just started up a little differently. AOMP is our research compiler that is testing things out for the actual release. And you can build that. We are not doing that currently because we're using this new AFAR drop with the Fortran compiler in it. GCC, AMD funded GCC for a while to try to do offloading. And so there's a little bit of support in the GCC compilers, but it is not, the performance was not acceptable. So that path to getting good performance out of GCC for offloading was abandoned for the time being. So it does provide OpenACC support though, and if you want to run it on your local laptop, it may provide you with some capability to test code. So we're really recommending LLVM, AMD Clang, and HIPCC. Now, people get confused because there's another AMD compiler called AOCC, and that's the AMD optimizing compiler for CPUs, and we don't use that for GPUs. So we talked a little bit about the AMD Flang new compiler, and you can download that package. There's a blog post on how to access it and download it. It's just a tar file. You just untar it and set your compile paths to it. So it's pretty easy to put it on your system. And we've been doing that for a lot of different sites. Strongly recommend if you're working with Fortran. I think that was done on the MI300A. Is that correct? Did we get the AMD Flang new on the MI300A here?
Oh, so it is not installed yet, but I don't know. Probably any feedback.
Okay. Yeah, we strongly recommend that, and we have samples of how to set the modules for it if you want to do that. And it's pretty easy to install. So that would be, after you install ROCm, that would be the next thing I would recommend getting on the system. If you are at the 7.0 release, it's already built into the 7.0 ROCm. I still recommend putting this AMD Flang new on the system because it's a couple months later version of Fortran. This also, the AMD Flang new comes with much newer C and C++ compilers as well. So I would recommend use the ROCm 7.0. If you hit a Fortran bug, try the AMD Flang new. Doesn't work there, call Giacomo and we'll get it worked. We'll work with the compiler team. Okay. And the compiler team is prioritizing bug reports right now. They don't have a comprehensive test suite to say it's meeting OpenMP standard X. So they're working based on what functionality people are using. So when we compile for offloading, we use this OpenMP, which we use also on the CPU, but we provide this offload architecture flag. And if you use this flag down here for the architecture type, we have the MI300 is GFX942, but if we provide this, it will run on the CPU. So that can be a way to help you test the code. You can supply multiple GFX models separated by a semicolon. Okay. You know, some of the older compilers had much longer compile flags. It's been simplified to just these flags here. So you may see examples with much longer ones that are no longer necessary. Okay. That's kind of the, you see also the GCC versions as well, but that's kind of the mechanics to get it to compile. And for a OpenMP make file, we can detect the compiler and apply that offload flag. And rather than hard code in what GPU type you're on, we recommend something like this little shorthand command to grab the GFX model off of the ROCm info. So you don't have to hard code the model you're running on. However, if you're going to cross compile, you may still want to do that. And then it's basically, we just supply those flags and it compiles like any other program. This is CMake lists, and we'll talk a little bit more depth on this when we talk about ROCm and portability. But here we see we just need to set those flags for the compiler again. You also need to use those flags for the link step. That's something people always miss on OpenMP. So you have to specify the flags for both the compile and the link. Get the runtime library. So our first step is to just add a compute pragma to that loop. If we're on an APU, we don't have to worry about memory movement. So you pick the most expensive loop in your code. You want to get the fastest speed up right away to help build enthusiasm about the porting, because it can be very frustrating when you port your code and the code is running twice as slow after the first week. So we really suggest trying to get the parts of the code that are really the most compute intensive and work on those first. You may want to try simpler loops, or I even recommend the examples we have in our examples repository. Make sure you got a working environment, working compiler before you jump into a million line code. We have way too many programmers that say, oh, this looks easy, I'm going to start working on my million line code and get very confused about what's happening. You do want to test your loops to see if they are fine-grained parallel. And one of the tricks is to just reverse the loop indices, go in the opposite order. And if you get the same answer, you probably are okay, because you're not order dependent. Now the compiler is going to break that up and you have no idea what order it's going to do it in. This is CPU code. So we're just going to have this OMP parallel 4, and that's going to run it on the CPU and by threading that loop across multiple threads. Fortran example, same thing, and that's one of the nice things about OpenMP is that you get about the same syntax for Fortran and for C. Now, we call this here a directive. As in Fortran, a directive is a comment that you would normally ignore except when you have that compiler flag on. Technically, if we go back to the C++, it's called a pragma, but we often use those terms interchangeably. So this is technically a pragma, and this is a directive. So when we want to target a GPU, we have to add this target clause. And that target clause is going to say, move this off to a separate device for computing. And OpenMP is not very specific about what that device looks like. So it's trying to trying to keep a high level view of it and just say, offload this to my compute device. In C++, we can do a structured block using braces. In Fortran, you may need the target and end target to define the structured block. And this moves it to the GPU, but it doesn't run it very efficiently because it's only using one thread on one work group. So what do we need to actually make it efficient and use all the hardware resources? So we have to use this long command to tell it to use all the resources on the system, on the GPU. We'll go into detail on what each of those do. But for most of your work, you're always going to use that long command. It's rare where you actually have to do something that breaks that command up. So it's usually a one-liner before each loop. And that's the beauty of it. Now, the problem with it is you see this code and you see one line changed and it says, boy, that looks easy. I just changed one line and it's running faster. But to get to that one line code and make sure it is correct can take hours of work. So you got to watch out for management. They think, oh, that's easy. It's not always as easy as it looks because you have to think about it. So here we have this part is being run on the host, and then we move that target directive is going to move it over to the device, and then we're going to return to the host. So we have to start thinking about what is on the host and what is on the device. And implicitly, the compiler, if it can see everything that's happening, will do this memory movement for you, even without HSA XNAC. It can see it's in the same file. It can see where the allocation's being done, and it will move these arrays for you. So when you enter the loop, it's going to move X and Y. And when you exit the loop, it's going to move X and Y. So in this example, we're going to export HSA XNAC equal 1 so that when it hits the page fault, it's going to move that memory. Now, this is an interesting note down here. In Fortran, allocatable arrays, the Fortran compiler knows its sizes, and so it knows how to map them. If they're pointers, it doesn't know. Or if it's in subroutine, it may not know enough information to move those things automatically. The SIMD clause in the standard was introduced, which SIMD means a single instruction, multiple data, basically vectorization. And there's only 2 levels of parallelism on the GPU. And so the vendors differed on how they treated that SIMD clause. And so it isn't necessary for AMD. It's not necessary for NVIDIA. But there are compilers that still use it, like Intel. Intel used to use it, but they have dropped it as well. So, or in the process of dropping it. So if you use the SIMD clause, you're going to get warnings, but it makes it more portable. In recent OpenMP offloading standards, they've added a simplification for all of this. You can just say loop. This is somewhat inspired by OpenACC, where the directives are simpler. And the first standard, it was you had to use OpenMP target teams loop. NVIDIA didn't use teams, even though the standard said you had to have teams. Well, actually, does it make sense that you have to have teams? We'll go into that in a little bit, but it probably doesn't. So now the standard allows either one. Okay, with OpenMP 5.0 standard, I believe. So you can do OMP target loop or OMP target teams loop, and it makes it much shorter. Okay. There's slightly different meanings of it actually in the standard, but the AMD compiler does exactly the same thing as if you had that long directive. So this is just simpler, much easier to read. And you often, if you use that long set of clauses, you can get a typo or get them in the wrong order or something crazy, which really isn't worth having that long directive. And loop, I believe, is in this the Fortran compiler, the recent version of the Fortran compiler. I have a test in for that. I need to verify it, but I believe the loop clause is working, or it will be shortly. Okay. Probably the most other common clause you're going to use is a collapse clause. So if you have nested loops, which we often have, 2 and 3D problems, we're going to have nested loops. You can collapse across all those loops, which gives you more parallelism, especially if one of those loops is 1 to 3. You usually want the largest dimension on the outside, but here, if we can just collapse them, we don't care. And the new development is, it used to be they had to be perfectly nested. You were not allowed to have anything in between the 4 statements. Now it will allow you to put something in between. I believe only simple things, but generally the kind of things you want in between the loops are fairly simple anyway. So that allows us to collapse even something like this with a small statement in between loops. And perfectly nested means there would be nothing here and nothing at the end here. Breaks missing on that. No, it's single line. It's actually correct, but I don't know the syntax. There was no opening brace here, so there doesn't need to be a closing brace, but that can be a little confusing. Okay, so here's an example of collapsing 2 do loops, and that could mean that there's a lot more parallelism you can work on in the GPU. And really, I consider our job as programmers, as scientific programmers, to expose the parallelism. And it's the job of the compilers and the operating system to make it fast. So our job is, we actually have to expose thousands of independent work items for a GPU. We'll get into that in more detail as we go on.
In the previous example, is there a shorthand also for it should be a parallel do before collapse, or that has to be written out?
We could do a loop
as well.
We could do a loop as well.
Okay.
So we could shorten this and then just add the
collapse to that.
Yeah.
Okay.
Yeah, so it's basically equivalent to put the loop. So loop would replace teams, distribute, parallel do. It actually gives the compiler more flexibility than all those clauses there, but in effect, it does the same thing. Yeah, and otherwise you're going to run out of room on your line with those long clauses. So on discrete GPUs, the data transfers are what kill you. I think everybody starts trying to program GPUs by offloading a loop, and the data transfer across the PCI bus here is going to take as long as the speed. It may even be slower to transfer that data than executing the loop on the GPU. And so you really have to start optimizing those data transfers. And this is where the MI300A makes this a lot easier. In the OpenFOAM code, one of our GPU programming experts, they went in and put these directives on about a dozen loops and sped up the code by 4x. And it's because they didn't have to worry about memory movement. So MI300A, you could just pick what loops to move over. The other thing with the MI300A is you can do shorter loops on the CPU with no penalty. This data transfer. So you may want smaller loops on the CPU. So you can do a very large operation on the GPU, and then let's say we got a halo or a ghost cell exchange on that we want to do. It's of order 100 elements I got to process. I can do that on the CPU, and it may be faster. That has not been heavily exploited yet in most GPU codes. Most GPU codes are still programming as if it were a discrete GPU. Okay, so here we see we have a pointer type in C. It doesn't know the size, so you have to put those map clauses in there. Because it sort of knows it's got to map the array, but it doesn't know what the size is. Fortran, this is one of the differences between C and Fortran, is C, you don't have sizes. In Fortran, you have something called a dope vector. Does everybody know what a dope vector is? Yeah, this is why I have gray hair. I was around back then. Dope vector is slang, and it's slang English, which is making it even more difficult for you. But it's give me the dope on the vector, which is 60s slang. It means give me the information about the vector. So when you pass an array in Fortran, you're not just passing the pointer, you're passing the sizes and the stride. That's called a dope vector. So Fortran has more information in some cases and can do this for you because it knows the sizes. So in Fortran, we could just say map X. I don't think that gets it. So the key in OpenMP target offload programming is that we want to reduce the data movement from the CPU to the GPU. So you can create large memory regions as well as compute regions. In the memory region, I'm going to map the data over at the start of this whole block and then bring it back at the end. But I can do a lot of compute loops in the middle here. So I'm going to map once and then do all these operations. And these routines, we'll do a presence check and see that the data exists, so you don't have to do anything there. You just do the compute directives. Okay, so this is called a structured block. And the reason it's called a structured block is this map goes from that brace to that brace. Okay, so it's a structured region. That doesn't work for object-oriented programming because you don't have a structured region. So later version of the OpenMP standard created unstructured data regions. And now you can use this enter data clause to say, I'm going to move at this point, I am going to move the data. And in an object-oriented form, you would do your allocations, immediately do the enter data. And then just before the freeze, you would do the target exit. Okay, so that whole region, anything between those two, but it doesn't need to be in the same file. It could be when you create the object and destroy the object. And so this fits larger programs. You don't necessarily have those allocations and deallocations in the same file. Okay, so unstructured regions really made OpenMP much more powerful for large programs. Okay, is that clear, the difference in structure?
But this is not required for the MI300A, unified shared memory system.
Yeah, so unified shared memory, what could we get rid of? It's gone. Makes it a lot easier, doesn't it? Just don't have to do it. Now, some people will, after they're porting, they'll put these back in so they can run on discrete GPUs as well. But they want to do it at the start of the program and the end of the program. And then it can also be a little bit faster to do discrete memory movement because it doesn't have to intercept every page fault. But it's just so much easier to program. You just don't, half of what I'm going to talk about here, you don't need, because I don't need to worry about memory movement. We had somebody ask, why do you show us all how to do all the memory movement? Then you tell us we don't need to do it. And there's a lot of truth to that. And so update will move the data. This is not mapping it, but it says I'm going to, at this point, update the data from one location to another. This can be effective if you have the most current version of the data on the GPU and you want to do something on the CPU. On the discrete GPU, that's going to come with a transfer cost though, right? So this is an example of where you might use that. Here, we read in new values on the host. The data was already on the GPU, so we have to update the GPU with those values we just read in. So here's a review of that data movement management. So you have to map the variables, and if you look at the code that you're operating in these simple examples, you can optimize it to only move the data you need to the GPU and only the data you need back. This is not easy in a complex program because it may take 3 or 4 paths and you're trying to figure out, well, what do I need on the GPU? It can be very, very complicated. And this is where that MI300A really helps you. And then you've got structured data regions, unstructured data regions, and then you can explicitly move data back and forth. This is sort of the same slide you showed at the beginning with the APU programming model as a reminder. And we just get rid of all those map clauses. That's a lot of work for those that you save. So you can do these exercises as well. I think let's take a break now, do the exercises. Let me pull up where we are in the schedule. Check the break. Yeah. So there's a good question. Can the object files LLVM and GCC be mixed? Actually, everything on the system is basically GCC, right? So you got to be able to mix them. But I want to warn you about that. A consistent tool chain is really, really important to make sure you're not running different versions of the C++ standard library, and actually LLVM uses the GCC standard library. But if you get different versions of that, you may get some strange things happening. So we actually work really, really hard, like on this system you're going to get on. We work really hard to try to make the tool chain consistent. So for example, we'll compile OpenMPI with GCC, but then we force MPI-CC to always be using the compiler you choose. So you don't want to start mixing GCC 13 and GCC 8. I should say G++. C is pretty portable code. It's C++ and Fortran, you get into trouble. Yeah. So they will wake, but we do get issues with that from time to time. And it's usually with big programs where that usually causes issues. And of course, those are the hard ones to debug too. Okay.
So would you explain a little bit about the XNAC equal 1 for MI300A?
Right, so this was confusing to me at first too. Why do I need HSA XNAC equal 1? I still need to grab that. So the GPU hitting that memory address is going to page fault because it's not on the GPU cache. So it page faults and it gets handed that single address pointer to populate the cache. It doesn't have to move the memory, but it still has to load it into cache.
Okay, thank you.
Yeah.
Another question is there's a way to write a portable program for the distribution within the unified shared memory.
Right.
So if you use the map directive, the memory probably should be moved even in the unified memory.
Right, so I can write the code in OpenMP, so I have device memory and host memory with a map. It will both be in the same HBM memory, but two different places. And the copy is really fast because it's on the same device. So, but I'm only using half my memory because I got a copy of every array. So that's not the best long-term plan, but it may be the way you get portability. Move the code over first and then optimize it later by eliminating that second copy. Yeah, it gets a little confusing.